having discussed about human eye, let's try to understand more into how we perceive the linear dimension, or rather the magnification or the uh, amount of size or the length, width and breadth of any object which we see around us. So what happens is, our retina is the screen which is used for every activity and for even the formation of images. So if we think of the human eye somewhat like this, this is the bulge, which is cornea. This is not a perfect diagram, just a representative diagram. Now, this screen over here which you see is a retina. And this bulge is the cornea. This is your cornea and this is your retina, this whole surface. Now, if there's an image here, it would subtend some angle, right? And this angle is known as your visual angle. Now, the idea here is the amount of rods and cones which this image would activate would give the brain signal to identify the length, height or breadth of the object or the dimensions of the object. So because the retina has rods and cones, and those rods and cones are helping my brain to identify the dimensions of the object, more the retina is covered with the object, more would be the size of the object which my brain would perceive, rather my eye would perceive. I would personally prefer brain here because your eye is just a device for your brain to perceive the dimensions of an object, and retina is the medium. Now, the same object, if you take it, let's say, far away, what would happen is this object would now subtend a lesser angle and use a lesser space of the retina, which means a lesser angle is congruous to telling a lesser space in the retina or on the retina. And if lesser space is occupied by the image, what happens is lesser number of rods and cones are activated, which means the brain would perceive the image to be of a lesser dimension. The same object, if taken far away, my retina would give the signal to the brain that the object is of a lesser dimension, which means the magnification reduces if I take away the object from my human eye, or rather any eye for that matter. What happens if we bring it closer? It's not difficult to understand that naturally it would occupy a more space on the retina, the visual angle would increase. So I can sum this up as visual angle gives you an idea of the dimension, and this is what magnification is about. If I can somehow increase or manipulate my visual angle, I'll have a magnification of the object, or I'll see a magnified image. Now over here, I have a lot of optical instruments which does the same work. They manipulate the visual angle to produce a magnification, right? Now, let's say you're just seeing an object and you cannot bring that object closer than your least distance of distinct or clear vision. So that is the limit which our human eye has. It cannot magnify an object beyond a certain point, because my visual limits are from D to infinity. I can see from D to infinity, which means on an average basis, a normal human being can see an object situated from D to infinity. D is your least distance of clear vision or distinct vision. Least distance of distinct vision. And by this logic, this diagram says that the closer the object is to the eye, the higher the size of the image would be on the retina, and my brain would perceive that the object is of a larger dimension. So I have to bring that object closer to my human eye. Now, I cannot bring it closer than D. So that is putting my limit on magnification. So whatever the object's height is, let it be h, I cannot bring the object closer than D, which means I can only have an angle, visual angle theta naught equal to h upon D. This is the limit of the, or the restriction of the eye. This essentially is the visual angle which you would see for maximum size of the object, or rather the image, and you cannot make the size greater than this situation. Now, I have optical instruments to achieve it, to magnify the object's image greater than this. So let's look at one of the optical instruments, a simple microscope. A simple microscope essentially is a convex lens, or rather a converging lens. I won't say convex lens because convex lens essentially is about the geometry of the lens, and as we have discussed in the previous videos, that the geometry of the lens has got to do nothing with the converging or diverging property. It has to do with refractive indices of the medium and the lens too. So when I say converging lens, what I mean is it converges the rays, and all the parallel rays coming to the converging lens would intersect at the focus point, right? So what I do is, a simple microscope essentially is a converging lens just placed in front of the human eye. Now this is the magnification my eye can produce. Now let's see what a microscope can produce. Now, if you have a microscope over here, it is essentially a converging lens. See, I'm using a biconvex or equiconvex lens over here, but it doesn't mean that it is a converging lens necessarily. But for our purpose, I'll just say that this is a converging lens, because geometrically, and if the refractive indices are of the normal property, then this is obviously a converging lens, a convex lens under normal circumstances. So let's say this is the situation. Your object is located here. What will happen is, let's say I've somehow brought simple microscope in such a way that the object is now at my focal plane, right? So what will happen is, this ray would converge in this direction, and this ray which passes through the optical center would go unrefracted, and they would be parallel to each other. Why? Because that's the property of focus. Rays originating from focus, after refracting from the converging lens, they become parallel to each other. So this now is parallel. So if I place my eye over here, see, I'm not drawing the eye diagram because that doesn't make any sense drawing it again and again. Just keep it in your mind that there's an eye over there. And whenever the eye sees that the rays are coming in this direction, it tries to reproduce them backwards. And now it would think that the rays are actually coming from infinity, because parallel rays give the information that the rays are coming from infinity. And whenever infinity is to be seen by the eye, or parallel rays are coming to your eye is under least strain. It is, the ciliary muscles are the least strain at this position. And this kind of situation is sometimes known as normal adjustment. Normal adjustment. Now, if you think of it, before the simple microscope, this was the magnification, or rather the visual angle, which I could have attained. I should not say magnification because that is a misnomer over here. This is the visual angle which I could produce. If I use this converging lens, this essentially is the visual angle which I can achieve, this theta, right? And what exactly is this theta? This theta is equal to h upon f. Why? Because this length is the focal length, which is f, and this, in this right angle triangle, this is h and this is f. So h upon, this is just h, this is f, h upon f. The same angle would be coming over here, the same would be going to your eye. So this is the angle, the visual angle perceived by the eye at this position. So this is what my convex mirror has achieved, and this is what my normal eye could have achieved. So magnification is always defined as what I have achieved by that optical instrument and what I can achieve without that instrument, which is theta naught. Now this gives you theta is equal to h by f and theta naught is equal to h by d, and this gives you d by f. What is d over here? D is the least distance of clear or distinct vision, and f is the focal length of the simple microscope or the converging lens. I'll just write a simple microscope term over here because that would make things more clear and remove away the ambiguity over here. This is a simple microscope. The C and O are somewhat looking like cousins, which they apparently are. Now, this derivation was for normal adjustment. Now, I can also try to bring this object more close. Why I would do that? I would always try to do that because that would increase my visual angle, and that is the task of this instrument, to increase the visual angle, because that would increase the magnification, right? I'll just write a magnification thing over here. That would make more sense. This is your magnification. See, the idea here is you don't need to see the letters clearly, you should feel it, that this is magnification. What are the spelling over here is, you don't need to be bothered about whether it's visible, legible or not. And this formula is for normal adjustment, when my eye is perceiving the rays to be coming from infinity. But I can further bring this converging lens closer to the object, and if I do that, I will have a larger theta, and that essentially would give me a larger magnification value. But there's a limit to what I can do. Why? Because let's try to do that first. Why there's a limit to it? This again is the same lens which I'm using, the converging lens. This is your f. I've brought the image object closer. So let's say this is your same length, right? So I'll measure with my hand. It's not perfect, but yeah, it does the work. Now, this ray goes like this. This goes like this unrefracted. And this ray over here, as this is not on the focal plane, this won't become parallel. Does it go like this? I hope this is clear. So these two rays now are not parallel. So am I over here, the task of I is to retrace the rays. So what it will do is it would try to retrace them like this. And it will perceive that these rays are actually coming from this point, which means this guy over here, this tall guy, is the image which my eye would see. Now, this length over here is your h prime or h dash. This is your h. Now, my eye can only see objects between d to infinity. If I bring this more close to the lens, even this guy over here would be closer to your eye. And I cannot bring it closer than d, which means the limit on this is d. See, you could argue that I is here and d is here. But essentially, this is this is basically an exaggerated diagram. Your eye won't be this far away. Your eye would be just here itself. Just for the sake of understanding purposes, I've made this diagram in such a way that you feel that d is only till here, why my eye is here? But your eye essentially is here only. It's not here. I'm making it to have better visualization of the situation over here. I'm exaggerating this distance, right? So this has to be d. Now, let this be some u naught. Now this u naught, d, and the focal length, let's say this is f, are just numbers. They are not any sign convention number. They are just numbers, right? So if I have to find out now relation between all these things, I have to use my lens formula. Why I do need to have relation on these things? Because now when you check this angle out, this theta essentially is what I'm after. This theta is equal to h upon but I don't know h. If I divide this upon this, what will happen is I'll get a d by mu naught, right? Magnification is equal to theta upon theta naught. So this by this gives you d by mu naught. I don't know mu naught. How can I find the magnification for this situation? So I'll have to use my lens formula for that to understand what exactly mu naught is. Let's use that. So I know my lens formula very well. 1 upon v minus 1 upon u is equal to 1 by f. This is image distance, object distance, and focal length. Now in this situation, I know that my v is d with a negative sign because it's the left of the optical center, or rather to the left direction, the opposite direction of ray travel. What exactly is u? Again, u also is of a negative nature, so minus u naught. See, u naught is not with sign convention. U naught is just a number, so I'll have to use a sign convention for that. And as this is a converging lens, the focal length has to be positive. Correct? Now, 1 by minus d would be equal to 1 by minus u naught plus 1 by f. On further manipulation, what you will get is 1 by mu naught is equal to 1 by d plus 1 by f. I've just rearranged the terms. Now what I need is d by mu naught. U naught, sorry, not mu naught, u naught. This is u naught. So I need d by u naught. Just multiply d all over. What I will have is d by u naught is equal to d by d, which is 1 plus d by f. Now here you have a breakthrough. You have got to know the value of m, and you have now the value of m, which is this thing. So magnification, just plug in this value from here to here. What you would get is m is equal to 1 plus d by f. Now this thing over here essentially is the formula for magnification, and this is for the situation when I have brought the image closer to the lens before the focus or focal point, and this is a greater magnification than the normal adjustment case. So this formula is for normal adjustment, and this formula 1 plus d by f is for the situation when my eye is seeing the object at d, or rather the image at d, not the object but the image of object at d. So I cannot achieve magnification beyond this. That's the limit on my eye. Now naturally speaking, my f should be less than d to have any meaningful magnification. Only that would give me greater than 1 value. Mathematically speaking, this feels that I can make f very small and magnification very large. But that doesn't work always. Why? Because the moment you make the focal length lesser and lesser in order to increase magnification, what happens is there are some irregularities in the lens construction. Some kind of misinterpretations of the formula, of the lens formula and all. And those things doesn't make the image clear, and we lose the clarity and the precision which we were after. So essentially what we do is we don't pursue any magnification more than 4 to 5 times. So anything around 4 to 5 is okay for us, and that is the job of a simple microscope.